compute these splines is not in the exam material, but the idea of how the splines, what they are and how they work, is in the exam material. Okay? Okay, so this, I have replaced the slide set that was in the resources file in Sakai with this one. So realize that this is in the exam material. Next, also I have put on resources slides summarizing the material to today. That is to say, the material that will be covered on the exam. You have two choices of when I present that in lecture. And I'm going to take a poll right now by show of hands. The choices are as follows. Neither one is ideal for you, perhaps. But anyway, one possibility is I do it immediately. That is to say, next Tuesday, okay, while the material is still fresh, okay? The other is I do it at the last available time before the exam, which turns out to be still almost 2 weeks before the exam, namely on the Thursday before spring break starts. Right? You understand? I can do that summary next time, or whatever it is, the teens of March on that Thursday before spring break. After spring break, the next lecture, I will be spending time taking questions on the exam, the sample exam or exams, and generally making sure that all the questions on the material are done, and then the exam will be in the second half of the week after spring break. Okay, so how many people would prefer to, while the material's fresh, to see the summary next time? I see 2 hands. How many people would prefer to see it nearer to the exam time? Lots, okay? So we will do it that time. Okay, but meanwhile, the slide set is online. If you want to go look at it independently, you're welcome to do that, obviously. Okay? Okay, so we were talking about the idea of apertures and levels of detail. And I want to make that a little bit clearer with reference to four of the main four, actually, of the alternatives for this multi-scale analysis. So, in multi-scale analysis, we have aperture size. We can look at the whole image, for example, the image in the upper right, as a whole, with one big aperture covering pretty much the whole image, which would not respond very well with regard to, for example, the locations of where the object in the middle of the image is. We could do it at apertures maybe half that width, which would respond better to the overall thing, but not all that well to some of the details in it, like this little lobe here, right? Wouldn't get very well dealt with at that scale, or smaller scale yet. Those are aperture sizes, right? When we're talking about a Gaussian aperture, we're talking about an aperture which is a measure of the width of the Gaussian, a sigma, for example. Okay, we also have this issue of levels of detail. So, within an aperture, if you use the sinusoid under a Gaussian envelope, like you see here plotted, or like you see here as an image, you can talk about the wavelength between the, say, the tops of the lobes of these, and you have various possibilities for that, right? So you can have a wavelength which is essentially proportional to the aperture, or half the aperture, or a third of the aperture, right? So you get different frequency sinusoids that you're using. The higher the frequency, the smaller the level of detail, right? We will see that it doesn't make all that much sense to use really very small levels of detail with big wide apertures, right? But that's not our problem right now. The basic thing I want you to understand is this issue of aperture size, which in the case of a Gaussian is the width of the Gaussian envelope, if you will, and there's levels of detail. Now, one of the options that we have talked about, important options, is the Gaussian derivatives as levels of detail. So the zeroth derivative, the Gaussian, is one has a large level of detail. The first derivative of the Gaussian, the same Gaussian, so it has the same aperture, but it's a first derivative, has the next level of detail. The second derivative is the next smaller level of detail, and so on, so that the order of the Gaussian derivative forms that characterizes the level of detail. And so if we look at a Gaussian of some width, this is the same width, this is the same width, but the first derivative is a first derivative of a Gaussian, which is the operator here, and it has, as you can see, a single zero crossing and two lobes, whereas the zeroth derivative has only one lobe, right? One relative max or min. The second derivative has two zero crossings and three lobes in the same, roughly in the same width, and so on. And you can play the same game with the Gabor wavelets if the theta is measured relative to the aperture width. So you can have cosine theta, or half the wavelength, or a third of the wavelength, or so on, under the same Gaussian, right? The Gaussian of width sigma. Okay, so you see that, for example, in this Gabor wavelet function shown here, if we have a particular Gaussian, and we have however many periods there are under this Gaussian here, and if we widened the Gaussian, we'd have a bigger aperture, and we nevertheless could keep the same wavelength or make the wavelengths move in proportion, because the level of detail essentially has to do with the wavelength as a multiple of sigma, if you will, a submultiple of sigma. Is it clear what I'm talking about? Any questions? Okay, one of the very interesting things is, okay, so point is that the number of zero crossings of just ordinary Gaussian within some range, they're comparable. So if you double the wavelength, you double the number of zero crossings, half the wavelength, you double the frequency, you get twice as many zero crossings. You triple the frequency, third the wavelength, you get, again, 3 times as many twice. It's 0, 1, and 2. I'm sorry, I got off by 1 in what I just said. But the main point is that there's not all that different looking between this thing and a Gauss and a cosine function that looks like that, right? The first derivative of the Gaussian and the sinusoid at the corresponding frequency or the corresponding wavelength doesn't look all that different. Here, you know, it's a little different. It doesn't have exactly the same zero crossings, and it doesn't. These lobes are lower than here, but nevertheless, you get pretty comparable looking kernels from the Gabor wavelets and the derivatives of the Gaussian. And indeed, experience bears that out. The features that you end up measuring of the image data that you get by using the Gabor wavelets or by derivatives of Gaussian are quite comparable, right? The main issue is what's the level of detail and what's the aperture width. Okay? So far, so good. We've been talking about the different levels of detail for a given aperture width. But I also suggested we're going to want to take various aperture widths, and corresponding to the different aperture widths, we're going to want to have this different spacings of where we measure within those apertures. So over here in the blue, I've shown apertures of some width. Each one of these circles is intended to be maybe the 1 sigma away from the center of a Gaussian, centered at the middle of the circle, and I've shown 4 apertures by 4 apertures, the blues, and they overlap, right? So now you have 16 blue apertures that you might measure, within each, whatever levels of detail you want to measure. Okay? And but I suggested earlier that we might want smaller apertures to measure smaller features in the image. And so we're going to need to sample those, for example, twice as densely as here. And now we have 8 apertures by 8 apertures, and I haven't drawn all the reds because besides being complicated, it made the figure hard to understand. Okay, you understand you can measure, when you have apertures, the whole idea is to be able to get locality, which means you have to put them down at various positions spaced along the image. Okay, and within any aperture, let's talk about the derivative of Gaussian as what we want to choose, although we could equivalently choose the Gabor wavelets. And your choices in 2D are at full aperture, whatever we mean by that, global aperture, let's say. You use the Gaussian. At the same aperture, you get the first derivative in x and the first derivative in y. Obviously, that allows you to compute directional derivatives in any orientation by dot products with directional vectors. And thus, it allows you to compute edge strength at that aperture width, right? Because gx and gy, we saw, were good for computing edge strength. And then you can compute the 3 second derivatives in the cardinal directions, gxx, gxy, which gets used twice, and gyy. And likewise for if you wanted third derivatives, you'd have xxx and xxy and xyy and yyy, and those repeat themselves in various places in the tensor. And you'd compute those for a given aperture, and for another aperture, you would do the same, right? Well, how do you think and someone proposed for if we wanted to do this for multiple aperture sizes, and we wanted to compute, let's say, all 4, 3, 7, 2, 9, all 10 of these levels of detail contributors. Of course, in 3 dimensions, you'd have a GZ as well in the first one, and XZ and YZ and ZZ and so on in the second, and so on. But let's just talk about 2 dimensions. How would we go about, someone suggest, how we would go about computing the values that we wanted here, and do so in a reasonably efficient fashion?
You could go into the frequency domain since the derivative is like a multiplication there.
Well, we've got convolutions to take the derivatives, which are best done in the frequency domain. Absolutely right. So we'd want to go over into the frequency domain and do these multiplications by 2 pi I nu and that squared and that cubed and so on, right, in the frequency domain. But what's the operation being done for this of a Gaussian? It's not a convolution, it's a multiplication within the aperture. And so those most conveniently would be done in the space domain, right? So you could compute the pure derivatives once and for all, okay, at, if you will, pixel resolution, and go over the frequency and bring them back. But now you'd need to multiply by the Gaussian centered here at this width, and 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 so on for all the blues. And then likewise for the smaller standard deviation Gaussians for these red circles, and so on. Okay? But the upshot is we could get computations with locality. And if by some chance we happen to know that we're only interested in some particular part of the image, we don't have to compute some of these. If we're interested only in this region of the image, we wouldn't have to compute the red ones down there. Okay. Questions? Okay. So, so far, I've said that for computational reasons mostly, you would either do this or this because you get roughly the same results. The derivatives of the Gaussian, what can I say, are a little bit, I want to say this, it's Taylor series-ish, except instead of polynomial basis functions for the basis images, you're using Gaussians to indicate how far you are from the center of the aperture. Okay. Okay, fine. We have another family of possibilities, the general approach for which I'm going to lecture about now, and the details of which I'm going to lecture about after material for the exam closes. And they are the orthogonal wavelets. And as functions in 1D, you see two of them here. The properties of the orthogonal wavelets is that you have a single function. You choose one base wavelet, the global wavelet. Okay? So let's say this is this is a base wavelet. It covers a region sort of from here to here. Right? And it's centered at the middle of the image, middle of a one-dimensional image. It's applied separately so that you do it on X and then you do it on the result in Y. But let's just talk about it in one dimension. Once you have that function, and not all there are a very specific set of choices that are possible. Once you have that function, you can simply scrunch it by a factor of 2. Precisely a factor of 2. Not 3, not 5, 2. They're binary multiples of 2. Okay, so you scrunch it by a factor of 2. And instead of placing it at this center here, you place it in the center of this half and the center of that half. So you're making you're dividing your space just like I talked about here, except into halves in each dimension. Right, so it's and you have one of these guys in each dimension, right, in X and in Y, at each of these 4 positions, or in one dimension in each of 2 positions, spaced apart now by half the width of the image. Okay? So when you do that, the wavelength changes too, right? As you scrunch this function, this kernel, if you will, by a factor of 2 down, the wavelength is also halved. The coverage is halved, the aperture is halved, and the wavelength is halved. And we're going to see that this idea of having the wavelength change in proportion to the aperture is going to be a pretty good idea. Okay, then you play the same game all over again. You halve it again. Not third, half. So now we're a quarter of the original wavelet, right? So we have 4 of these guys. Scrunch in a long direction by a factor of 4. And you're going to place them here, 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 and here. That is to say, centers of quarters across the image. Okay? And then play the same game with eighths. Right? We scrunch it by a factor of 8. And likewise, the wavelengths change by the same factor. And they're placed in the middle of eighths of if you divide the whole range of the image into eighths, and then the centers of those will be at 1/16, 3/16, 5/16, 7/16, 9/16, and so on, right? The beauty of this particular arrangement is that if you choose your original base wavelet right, all these different scrunched wavelets at various positions are orthogonal to each other. They provide orthogonal basis images. We know what the advantage of that is. It makes it really computationally easy to compute their coefficients. And so when I say all, I mean the one that you had at full resolution, the two that you had at half resolution, they're orthogonal to each other and orthogonal to the one at full resolution. And then you have 4 more, for one dimension, 4 more at the next level of binary decimation. And all of them are orthogonal to each other and orthogonal to the ones at there were 2 of, and orthogonal to the one at 0, and so on. So they're all mutually orthogonal bases, which has certain advantages. And we'll see disadvantages of this arrangement as well. I'll just mention an important one. The orthogonally depends on the binary decimation, on dividing by exactly 2, 4, or 8, or 16. And so if you need scales in between them, there's a problem. There's also the fact that they're applied first in x and then in y, and that turns out to be not isotropic for the orthogonal wavelets. We'll talk about that more later. But you'd like isotropy. You'd like not to be biased these guys are biased to x and y, and not so good for finding features that happen diagonally, for example. Whereas the Gaussian and the sinusoids are isotropic. So they can be applied separately if you want to. But nevertheless, it's equivalent to apply to the same application in any direction. Okay, the last of these that I want to talk about is the spline approximation. Again, a multi-scale analysis with similar properties. And let me see if I can explain. This is the one that people find, of all of these, hardest to understand. So let me see if I can explain. You have your image. I'm showing it here. This is a, I don't know, a 256 by 256 image or whatever. It's a full, it's 128 by 128, it's 1024 by 1024, whatever you want. Okay, let's assume, though, that the width of the image is 2 to the some power n. The idea is that you can sample the image at some spacing that's going to be proportional to the aperture. So what's shown here is an aperture this wide and this high, right? And here's one of the pieces, and here's another one of the pieces. They're patches, and each for that where you have values at each one of the positions within a patch. So if we had a 128 by 128 image, then this would be, a patch would be 32 by 32 in size, right? In this particular patch size. A quarter. Okay. And for each patch, we're going to have a polynomial function that we're going to be able to evaluate at any point within the patch, at any pixel within the patch. Okay? It's going to be a polynomial function in x and y. It's also going to be developed separately so that you do it in x and then on y on the result. And I'll talk about that later. But the main point is, for each patch, you get its own polynomial. Okay? And the polynomial's coefficients are determined by surrounding so-called control points. So for this patch, turns out for the one we're going to be talking about, which is something called B-splines, let me write that was a juicier pen to be seen on the recording. What happens is that the coefficients of the polynomial here are determined by the surrounding 4x4 control points. So some values, some image intensity values at the blue surface for this blue square. Here, 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 and here. Okay, which is to say that the aperture the support, if you will, from which the data comes is this blue indicated double blue lines around it for that patch. Right? So the aperture is actually from which the data comes is that wide, and it's only used at a wavelength, I mean at a spacing, which is to say a level of detail determined by this width. This is the LOD, and this is the aperture. Right, the aperture is where the data comes from, and the level of detail is where you use it. So now you have another patch. This one, for example. Same size, but its control points are going to be around it. This, and this. The 16 control points are going to be there, and they're going to determine a different polynomial for this patch. Right? Every patch has its own polynomial, and they're determined by the surrounding control points. But notice that the control point values are used for different patches. So this particular control point value, whatever the intensity value is here, is going to have an effect on this patch, but with respect to the one that's at its lower right corner, whereas the same value is going to be used for this patch, but it's going to be the one that's in its upper left corner. Yeah? See how that is? So and now, the beauty of these guys is that if you look at adjacent patches, like this guy here and this guy here, it's arranged, the whole scheme is arranged so that this polynomial and this polynomial fit smoothly together. That is to say, at this edge separating the two patches, across that edge, the polynomials agree in value. They're smooth. They're in first derivative and in second derivative. They produce continuous functions in 0 first and second derivatives. So you end up with a smooth arrangement overall, and you end up with okay, so in the picture on the screen, intensity is shown as height, right? So you can see that if you think of intensity as height, it is producing a nice smooth surface. But of course, we're going to be using it as for intensities and not for heights, if you will. It's just to illustrate the process. But now notice that the same thing can be done at multiple scales. That is to say, instead of dividing the image into quarters are in one dimension, 16ths in two dimensions. We can divide the image into eighths by 8 by an eighth, getting 64 patches. Right? And now your aperture and your level of detail, the patch size and the size of the support have scrunched by a factor of 2. Just like it happens with the orthogonal wavelets where we scrunch by a factor of 2. And these as well, TOO, these as well are generated separably and are not isotropic. That is to say, they're biased in the x and y direction, in favor of the x and y pure cardinal directions. We will shortly be talking about how the separable computation works. But I'm trying to keep separate this idea of aperture size and level of detail and successively small apertures and small levels of detail from the actual implementation of all this. I am basically done with my overall discussion of the various apertures and levels of detail that we're going to be covering in this course. We still have to talk a lot about implementation, how that's going to work. And we're going to have another very important idea that is not covered on the exam, and that is the idea of residues. So that instead of talking about getting the information at some level of detail absolute, we talk about the information that has not already been covered at larger levels of detail, and only the difference of what's left to be represented at a new level of detail. Okay? That's in the post-exam period, which starts now, except that I want to take any questions you have so far on the ideas of aperture and level of detail and these 4 options that I've been talking about: the Gaussian derivatives, the Gaussian wavelets, the orthogonal wavelets, and the B-spline arrangements. No questions? Okay, then. Okay, you now understand. Everything I've said till now on this lecture was in the exam material. Everything I'm about to say is not. This is a diagram that refers to one-dimensional subdivision. It's applicable in 2 dimensions or 3 dimensions, but I want you to understand, just so that you can see what's going on. In images where you're looking at them pixel by pixel, what's the level of detail that you're capturing? How wide is the information of a unit piece of information, a single value, when you're looking at pixel values? 1 pixel, you got it, right? Absolutely perfect. The level of detail is a pixel. every location has the pixel value. But the point is, you really have no choice about the level of detail. If you want to think about the pixel as a delta image, as a multiple of the delta image, then the levels of detail for a delta image are what? Over on the frequency domain. All of them, right? The pixel value really understood as a delta function if you have frequency, that's the Fourier transform of a delta function. It exists at all frequencies, that is to say, at all wavelengths. So strictly speaking, the spacing, the aperture size, is what the answer was correct for the answer, okay? The aperture size is 1 pixel, but the levels of detail are really all levels of detail simultaneously. So, in other words, if you have a particular, these are indication of different pixels. 1, 2, 3, 4, 5, 6 pixels in 1D. And the point is each one of them covers all levels of detail, and you can't distinguish one from the other. And the next pixel, all levels of detail, and you can't. Okay, so this is the aperture, and this is the level of detail. All levels of detail, undistinguishable, right? If you are talking about objects and you have a bunch of sample points at some spacing along the object, the same thing is the case. The location of those points, in this case in 3 space, for this pair of lungs, give you the aperture size, and the level of detail is all scrunched together. All levels of detail are undistinguishable. Now let's look at the Fourier coefficients. The coefficients of the sinusoids that are our basis images. Now we distinguish levels of detail, right? We have one sinusoid at one frequency, sinusoid at another frequency. Each different wavelength is a different level of detail. We can distinguish them one from the other. The coefficients of a sine or cosine at one frequency is different from the one at half the frequency, which is to say, double the frequency, which is to say half the wavelength, and so on. But on the other hand, the location is global. We can't tell one place from another in sinusoids. The aperture is global. The level of details are distinguishable. Right? Neither one of those is particularly useful for multiscale analysis. What we'd rather do is something more like this. And this is what you've been seeing in these previous examples. You'd like to cover some small range of levels of detail with correspondingly sized apertures. So if I divide my image into quarters along one dimension, if I divide it into halves, so that I had something like that in 2 dimensions, I'm talking about halves here, right? And then those halves could be divided respectively into, well, the whole business into thirds, but also with a range of, a corresponding range of levels of detail that are undistinguishable. And then we can divide it into sixths. I probably should have made this picture with quarters and eighths, but okay, the point is generally made that as the whole idea is that the aperture width and the range of levels of detail are in proportion to each other. And on top of that, we have this residue idea. That let's not talk about these guys representing the information at that level of detail, but including but rather let's, if you will, represent the information that we get from these lower apertures, the ones that the larger apertures and corresponding larger levels of detail. And remove that representation if you want to think of reconstitute the image data at that level of detail with those aperture sizes, which are proportional to each other. Take that reconstituted, heavily blurred information and subtract it from the original image, leaving no more components at that level of resolution. And then do this analysis on what's left, on the residue. And then we'll reconstitute the image we'll subtract that out, the representations we get from this, and then we'll represent the guy at the next smaller level of detail with the correspondingly next smaller aperture on the remaining representation. Well, the way the orthogonal wavelets or the Gaussian derivatives or the Gabor wavelets or these B-splines applied recursively is exactly according to that scheme. So, in other words, if you talk about this smooth function that we saw there, corresponding to the whole image, we can subtract that smooth function from the original image. And now we get a new image that's removed the information at this larger scale aperture, larger level of detail as well, because they're proportional. And then we do this with the control points that we use for the half spacing. Okay, so this is divided into quarters in x and quarters in y. Now we'll have spacing eighths in x and eighths in y. And we'll use the control points there. Okay, so let's talk about what one of those would look like. So we're going to have patches that are this size. And the control points that are used for, say, this patch here are going to be ones at here, 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 here. Where do I have? point is, let's see. Here, 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 and here, here. Okay, the point is that the control points are together closer than they were by half in each dimension. But those polynomials are not going to represent the original image. They're going to represent the image after you've subtracted out the one from the larger scale. Okay? Yes?
How are the values of the control points determined?
Well, you've seen both choices in this course. One of them is you actually just use the pixel values there. The other is you use the values averaged over a corresponding region. Somewhat preferable to use the second, I believe. Okay? Very useful question. Okay. So you have this idea of residues in any one of these basic approaches. So this is sort of a general framework for any of our what I call detailed residue approaches. Orthogonal wavelets, Gabor. In the case of, for example, the Gabor wavelets, you would take basis function for the whole image, one big, and maybe just a couple of frequencies. Not the whole full range of frequencies, because small levels of detail with big apertures is not what we're allowing. Right? So we're going to have maybe this is not a good example. This is too high frequency. With this kind of an aperture, we would want something that looked like that. That is to say, had bigger wavelengths, bit corresponding to the aperture. You never really would use this. You'd use something that was at wavelength sigma, maybe wavelength a half sigma, possibly wavelength a quarter sigma, but not very many of them, right? And then you would conceptually reconstitute the image with the new, with the coefficients of those few wavelets, those few basis images, with essentially one locality. Subtract that out of the original image and take what's left, and now have your aperture, and likewise have your corresponding maybe 3 levels of detail in X and 3 in Y. And apply that to the difference, to the residue. Okay? But realize that this application can be built by taking the differences between the basis images at different scales, rather than having to actually subtract the image data. Right? So if I have one of these and one of these, two different ones. I should have drawn this guy in a different color. I could take the difference of the black curve and the blue curve and make it be a kernel. And that would be the same as taking the black curve and applying it to the image, and the blue curve applying it to the image. And then subtracting the two results, getting residues, okay? So we're going to have this game of creating these so-called residue kernels that are made from the differences, if you will, between the different levels of detail. Okay, so I'm sitting here with here we go, a black cap in my hand. Some of you who have come to my office may have noticed that I'm an unusual faculty member because I have a chalkboard rather than a whiteboard, because of my principle that if you pick up one of these, it should write. And that's true for chalk, and it's not true for one of these. Okay. I've been here long enough that I was here when the building was built. And we all got to choose what we wanted our offices to be, we wanted them to be laid out. And I said, I don't want a whiteboard, I want chalkboards, thank you. Okay. Anyhow, what I want to go on now is to talk some details of this whole approach and talk about their applicability. So let's talk about the splines next. You are going to have an assignment that asks you to compute some spline approximations. Okay, a fairly common use of spline approximations has to do with the fact, for example, that images may have different shading. So if I have lights only in one corner of this room, the folks over there are going to be seen with higher intensities than the folks over here, right? There's going to be variable intensity of the light source. And the actual intensities that come out in the image are the product of the intensity of the light source and the scene intensity. And we're not interested in the shading of the image. We're interested in each of your faces, feet, various other hair, various other properties. Yes? And so we want to remove the effect of the shading. And so if we have that the image is shading of X times the I desired of X, where the I desired is actually what is the image of the subject matters. What we'd like to do is compute a shading function and divide it into the image, and then do a multi-scale analysis on I desired. Right? Or whatever analysis we want to do on I desired. But how do we get the shading information? And the answer is, well, it's typically shading is very, very smoothly varying. It exists only at what corresponds to large apertures. The intensity over there is having a serious effect already over here. Big aperture on that light that was applied. And so typically what one does is one takes a large aperture, large level of detail application to the received image and calls that the shading image, and then does this division. Okay? Blur the hell out of the image. You get pretty much the shading. And divide it into this. And you will have an assignment where you will do exactly that. You will be using the spline to produce a shading image. And you'll divide it into your original image to get something that compensates for the shading. Okay? And you'll use the splines to get the shading image. Okay, so let's talk about how the splines are going to work. This is the slide in the whole of the course that when people sit down and try to use it, they understand it least. Okay, and so I'm going to spend a lot of time on making sure you understand what's in this slide. First of all, it's about one-dimensional splines. It's about dealing in a 2D image with only one row. Of the image, and we'll apply it to each row, or to each row that we want to. If we're talking about ending up with splines that are the ones that are were originally drawn here, that have these levels of detail, we're talking about this row, and that row, and that row, and that row, and only those rows, right? Clear so far? We're talking about row by row, and the rows are spaced apart by this patch size. In that row, we have four values, and the one second with respect, because of this, we're going to be computing a polynomial for that patch, the middle patch, in this example, with its 4 control points. One at each end of it. We call that position T sub I. Well, this one T sub I minus 1, T sub I plus 1, and this one T sub I plus 2. Okay? Later, we'll be talking about other patches, and this whole picture is going to shift, and T sub I will, in a later application, might be instead of being interested in this patch, we're interested in that patch, And now this is t sub I. And this is t sub I plus 1. This is t sub I plus 2. What? T sub I plus 1 and t sub I plus 2. The point is that this t sub I is an index that tells you where you are at the relative to the control points that you're going to use. There's the control points 2 away from the end of the patch, 1 away from the end of the patch. That's the ith one. There's on the other side of the patch, the I plus 1th one, and at the other end of the patch. And what we're going to do in this patch is we're going to compute a whole bunch of values of this polynomial. Why? Because we're going to need them for doing the wider dimension spacing. So if we had a 128 by 128 image, then we will end up wanting to compute at a 128 by 128 image, and we're going to need to compute Y patches at all of these at this spacing. And so we're going to need to compute these guys, we're going to be control points for the Y operations. So we have control points in X at some spacing, and we now going to compute control points at a finer spacing that we're going to need to get the spacing in the Y dimension. Okay, so now we have to compute the polynomial that we're going to evaluate at all these X values. And so we're going to consider a function on t, which goes from 0 to 1, which is the width of the patch. 0 at the left end of the patch, 1 at the right end of the patch, halfway along the patch. Okay, so the t values, if we're computing 128 of these, will be I think 1 256, 3 256, 5 256, and so on, separated 128 apart. Okay, but never mind. The point is whatever t values we want, they're going to be on 0 and 1. And so this thing is going to be evaluated for t minus ti. Okay, so sorry. T minus ti equals 0, and t minus ti equals 1. Sorry, t minus ti is it is 0 here and 1 here. It's the relative fraction of the way of a patch from ti. Okay? So this is t, and these are t's centered at t sub I. So the first thing you will see is that the polynomial we're going to compute, which is q sub I of t for the ith patch, is going to be a cubic. It's going to have a term t minus ti cubed, a term t minus ti squared, a term t minus ti, and a term 1, t minus ti to the 0. Right? 4 terms in a polynomial, a cubic. These are cubic B-splines. And it turns out then that the polynomials that you're going to want are the 4 basis polynomials. The first one is, from the first column, minus 1 times this, plus 3 times that, plus minus 3 times this, plus 1 times that. The next one is 3 times t minus ti cubed, minus 6 times t minus ti squared, 0 times t minus ti, and plus 4 times 1. You get 4 polynomials from that, right? 4 different cubics. one for each column. Got it? And now, those respective polynomials are going to be multiplied by the first one of them, the polynomial that came from this column here, is going to be multiplied by the control point value, not the control point location, but the value at the control point. In our case, that's intensity. But if you have three values like red and green and blue, then it will be a tuple. Red at that value, green at that value, blue at that value. You'll get three different splines. One for the reds, one for the greens, one for the blues. Right? So you're going to have control point locations here, 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 and here. And the value of the intensity, for example, you're going to have an I of Ti minus 1, an I at Ti, an I of Ti plus 1, and an I of Ti plus 2. And you're going to multiply the first of those i's by this first polynomial. And the second of them by the second polynomial. So they really end up as basis polynomials. The i's are the coefficients multiplied by the first basis polynomial that came from the first column. And this guy is going to be multiplied by the second polynomial. And those polynomials are expressly chosen so that you get this wonderful behavior at the patch boundaries. Right? And so if I had a division of, let's say, 8 of these, I would compute this group from Pi minus 1, I have this I, this I, this I, and this I. And then I'd go and compute 128 more of these for that, from this one, this one, this one, and this one. Same polynomials, but they're polynomials on a different variable because now they're relevant to the relative to this guy being Ti rather than this guy being Ti. Right? Because for that patch, for this aperture, this guy is Ti. Okay. Likewise, when I want to compute for this one, I'm going to use the image intensities from this, 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 and this to compute all the, let's say, 128 values here. Okay, once I have that, somebody should already have wondered what we're going to do about the edges, what we don't, where this box doesn't have a guy to the left of me. We'll get to that in a moment, right? I need a point. I need control points bounding my patch and 2 on either side, and that I have edge effects. But let's not worry about that right now. As a result of this, I'll get 128 spacing along this row. And if I apply that to the control values of this row, I'll get like so. Right, 128 values. For every one of those rows, I can get 128 values. If it's 128 you're after. And now I can compute y1s for each one of these guys as control points. So I have this guy, this guy, this guy, and this guy, which I can use for a y direction applied separately. And I can do that for each of the 128 columns for which I've computed control points in the x direction. I have computed in the x direction control points that will be used in the y direction. You see why you need an assignment on this. You will get one. Okay? But you're working on another assignment the previous, the one you're working on is relevant to the exam. The one that you will get will be not relevant to the exam as such. Although you're still going to need to understand the basic idea of spline patches, but just not how to compute them for the exam. We're done for today. Any questions before we leave? Yes.
So the QIFT, for clarification, is that supposed to be the spline, the B-spline? Is that how it's-
Yes, the QIFT is the B-spline value. You evaluated at each of those values of T.
Okay, and then the matrix of integers, what is that supposed to be?
Those are the coefficients of the polynomials. 1, 3, minus 3, 1 is a basis polynomial, meaning 1 times t minus ti cubed plus 3 times t minus ti squared plus minus 3 times t minus ti plus 1 times 1. But this is really, I mean, that matrix works, by the way, if you think of multiplying it by these rows, row vectors and column vectors. Yeah.
This picture, where it says T is referring to the location, and then the T of I minus 1 is the interval.
Yeah, T is the location, T minus Ti is a fraction of the way you are along the box.
Okay.